Welcome to our deep dive into the fascinating world of artificial intelligence. Today, we're exploring the differences between machine learning and deep learning. These two terms are often used interchangeably, but they represent distinct approaches within the broader field of AI. Understanding their unique techniques, applications, and levels of complexity is essential for anyone interested in technology, data science, or the future of automation. In this video, we'll break down what sets machine learning apart from deep learning and why these differences matter in real-world scenarios. Let's get started by defining each concept and setting the stage for our comparison. Machine learning is a subset of artificial intelligence that focuses on building systems capable of learning from data. Instead of being explicitly programmed for every task, these systems use algorithms to identify patterns and make decisions. Machine learning covers a wide range of techniques, from simple linear regression to more complex ensemble methods. The key idea is that the system improves its performance as it processes more data. This approach is widely used in applications like spam detection, recommendation systems, and predictive analytics. Now let's see how deep learning fits into this picture. Deep learning is a specialized branch of machine learning that uses artificial neural networks with many layers, hence the term deep. These networks are designed to mimic the way the human brain processes information. Deep learning excels at handling large volumes of unstructured data such as images, audio, and text. It powers technologies like voice assistants, facial recognition, and self-driving cars. The complexity of deep learning models allows them to automatically extract features from raw data, reducing the need for manual intervention. Let's explore the core differences between these two approaches. Machine learning relies on a variety of algorithms, each suited for different types of problems. Common techniques include supervised learning, where models are trained on labeled data, and unsupervised learning, which finds patterns in unlabeled data. There's also reinforcement learning, where agents learn by interacting with their environment. Popular algorithms include decision trees, support vector machines, and k-nearest neighbors. These methods are generally easier to interpret and require less computational power compared to deep learning. Next, let's look at the core techniques behind deep learning. Deep learning's core technique is the artificial neural network, particularly those with many hidden layers. These networks can be feed-forward, where data moves in one direction, or recurrent, where outputs loop back as inputs. Convolutional neural networks (CNNs) are used for image processing, while recurrent neural networks (RNNs) handle sequential data like text or speech. Training these networks requires large datasets and significant computational resources, but the payoff is their ability to solve highly complex tasks. Now let's compare the complexity of both approaches. Machine learning models are generally less complex than deep learning models. They often require feature engineering, where experts manually select which data attributes to use. This process can be time-consuming but makes models more interpretable. Training times are usually shorter, and the hardware requirements are modest. This makes machine learning suitable for smaller datasets and applications where transparency is important. However, as the complexity of the problem increases, traditional machine learning may struggle to keep up. Let's see how deep learning handles complexity. Deep learning models are inherently more complex, with multiple layers and millions of parameters. They can automatically learn features from raw data, eliminating much of the manual work required in machine learning. However, this complexity comes at a cost. Deep learning models need vast amounts of data and powerful hardware such as GPUs to train effectively. The models are often seen as black boxes, making them harder to interpret. Despite these challenges, deep learning's complexity enables it to tackle problems that were previously unsolvable. Next, let's look at real-world applications. Machine learning is everywhere in our daily lives. It powers recommendation systems on streaming platforms, filters spam in our emails, and helps banks detect fraudulent transactions. Retailers use machine learning to predict inventory needs, while healthcare providers use it to identify disease risk factors. These applications benefit from machine learning's ability to process structured data and deliver interpretable results. The relatively low resource requirements make it accessible for many industries. Now let's see how deep learning is making an impact. Deep learning is behind some of the most exciting advances in technology today. It enables voice assistants to understand speech, powers facial recognition in smartphones, and drives autonomous vehicles. In healthcare, deep learning helps analyze medical images for faster and more accurate diagnoses. It's also used in language translation and even creative fields like music and art generation. These applications require processing massive amounts of unstructured data, something deep learning excels at. Let's compare the data requirements for both approaches. Machine learning models can perform well with relatively small to medium-sized datasets, especially when the data is well structured and labeled. Feature engineering plays a significant role in maximizing performance with limited data. This makes machine learning a practical choice for businesses and organizations that may not have access to massive data resources. However, as data complexity increases, the limitations of traditional machine learning become more apparent. Let's see how deep learning's data needs differ. Deep learning thrives on big data. The more data you feed a deep learning model, the better it performs. This is especially true for tasks like image and speech recognition, where subtle patterns can only be learned from vast amounts of examples. Deep learning's ability to automatically extract features means it can handle raw, unstructured data, but only if there's enough of it. Without large datasets, deep learning models may underperform or overfit. Next, let's talk about the hardware requirements for both approaches. One of the advantages of traditional machine learning is its modest hardware requirements. Many machine learning models can be trained on standard laptops or desktops, making them accessible to a wide range of users. This is particularly beneficial for small businesses or academic projects with limited resources. While some complex models may benefit from faster processors, most don't require specialized hardware. Let's see how deep learning's hardware needs compare. Deep learning models, on the other hand, demand significant computational power. Training large neural networks often requires specialized hardware like GPUs or TPUs, which are designed to handle the massive parallel computations involved. This can be a barrier for smaller organizations or individuals. However, cloud computing services now offer access to powerful hardware on demand, making deep learning more accessible than ever before. Let's move on to discuss model interpretability. Interpretability is a major strength of machine learning. Many models, like decision trees and linear regression, provide clear insights into how decisions are made. This transparency is crucial in fields like healthcare and finance, where understanding the reasoning behind predictions is essential. Being able to explain model outputs builds trust and helps with regulatory compliance. However, as models become more complex, interpretability can decrease. Let's see how deep learning compares in this area. Deep learning models are often described as black boxes. With millions of parameters and complex architectures, it's challenging to understand exactly how a deep learning model arrives at a particular decision. This lack of transparency can be a drawback in sensitive applications. Researchers are actively developing tools to improve interpretability, but it remains a challenge. Despite this, deep learning's performance on complex tasks often outweighs concerns about transparency. Next, let's discuss training time and efficiency. Machine learning models typically require less time to train compared to deep learning models. With fewer parameters and simpler structures, training can often be completed in minutes or hours, depending on the size of the dataset. This quick turnaround is ideal for rapid prototyping and iterative development. It also means that models can be updated frequently as new data becomes available. Now, let's see how deep learning's training time compares. Deep learning models, due to their complexity and size, often require much longer training times. Training can take hours, days, or even weeks, especially for very large datasets or complex architectures. This is why powerful hardware and efficient algorithms are so important in deep learning. Despite the longer training times, the results can be impressive, with models achieving state-of-the-art performance on challenging tasks. Let's move on to discuss the need for feature engineering. Machine learning, feature engineering is a critical step. Experts analyze the data and select or create the most relevant features for the model. This process can significantly impact model performance, but it requires domain knowledge and experience. Feature engineering allows for greater control and understanding of the model, but it can also be time-consuming. Let's see how deep learning approaches feature engineering differently. Deep learning models are designed to automatically learn features from raw data. This means that instead of manually selecting features, the model discovers the most relevant patterns on its own. This automation is a major advantage, especially when dealing with complex or high-dimensional data like images or audio. However, it also means that the process is less transparent and harder to control. Next, let's discuss scalability. Machine learning models are generally easy to scale for small to medium-sized datasets. However, as the volume and complexity of data increase, traditional machine learning algorithms may struggle to maintain performance. Scaling up often requires more sophisticated algorithms or distributed computing solutions. This can add to the complexity and cost of deployment. Let's see how deep learning handles scalability. Deep learning is built for scalability. Its architectures are designed to handle massive datasets and complex data types. With the right hardware and infrastructure, deep learning models can process millions of data points and continue to improve as more data becomes available. This makes deep learning the go-to choice for big data applications, but it also means higher costs and technical requirements. Now, let's compare the flexibility of both approaches. Machine learning offers flexibility in terms of algorithm selection and model customization. Depending on the problem, you can choose from a variety of algorithms and tune them to fit your needs. This adaptability makes machine learning suitable for a wide range of applications, from finance to healthcare. However, flexibility can be limited by the need for manual feature engineering and the challenges of scaling up. Let's see how deep learning compares in terms of flexibility. Deep learning models are highly flexible when it comes to handling different types of data, such as images, text, and audio. Their architectures can be adapted for various tasks, from classification to generation. However, this flexibility comes with increased complexity and resource requirements. Deep learning's ability to learn directly from raw data opens up new possibilities, but it also demands careful design and tuning. Next, let's discuss the cost implications of both approaches. Machine learning is generally more cost-effective, especially for smaller projects. The lower hardware requirements and shorter training times help keep costs down. Open-source libraries and tools make it accessible to individuals and organizations with limited budgets. However, costs can rise if large-scale deployment or complex feature engineering is needed. Let's see how deep learning's costs compare. Deep learning projects often require significant investment in hardware, data storage, and specialized talent. Training large models can be expensive, especially when using cloud computing resources. However, the potential for breakthrough performance in complex tasks can justify these costs for many organizations. As technology advances, the costs of deep learning are gradually decreasing, making it more accessible over time. Now, let's discuss the talent and expertise required for each approach. Machine learning requires a solid understanding of statistics, data analysis, and algorithm selection. While some models are straightforward, others demand deeper expertise in feature engineering and model tuning. Many educational resources and tools are available, making it easier for newcomers to get started. However, achieving high performance in complex tasks still requires experience and domain knowledge. Let's see what expertise is needed for deep learning. Deep learning demands a higher level of expertise, including knowledge of neural network architectures, optimization techniques, and hardware acceleration. Understanding how to design, train, and tune deep networks is essential for success. The field is rapidly evolving, so staying up to date with the latest research and tools is important. While more resources are becoming available, deep learning remains a specialized area within AI. Next, let's discuss the risks and challenges associated with each approach. Machine learning models can be sensitive to data quality and bias. Poorly chosen features or unbalanced datasets can lead to inaccurate predictions. Overfitting is another risk, where the model performs well on training data but poorly on new data. Regular validation and careful data preparation are essential to mitigate these risks. Let's see what unique challenges deep learning faces. Deep learning models are prone to overfitting, especially when data is limited. Their complexity can make them vulnerable to adversarial attacks, where small changes in input data lead to incorrect outputs. The black box nature of deep learning also raises concerns about accountability and fairness. Addressing these risks requires robust data, regular monitoring, and ongoing research. Now, let's discuss the future trends in both fields. Machine learning continues to evolve, with new algorithms and techniques emerging regularly. Automated machine learning (AutoML) is making it easier to build and deploy models without deep expertise. Explainable AI is another growing area, helping to make models more transparent and trustworthy. As data becomes more available, machine learning will remain a vital tool for businesses and researchers. Let's see what the future holds for deep learning. Deep learning is at the forefront of AI research, driving breakthroughs in fields like natural language processing, computer vision, and robotics. Advances in hardware and algorithms are making deep learning more efficient and accessible. Researchers are also working on making deep learning models more interpretable and robust. As deep learning continues to mature, we can expect even more impressive applications and innovation. Next, let's summarize the key differences between machine learning and deep learning. Recap: machine learning uses a variety of algorithms, often relying on manual feature engineering and structured data. Deep learning, in contrast, leverages multi-layered neural networks to automatically learn from raw, unstructured data. Each approach has its strengths and is suited to different types of problems. Understanding these technical differences is the first step in choosing the right tool for your needs. Let's summarize the differences in application. Machine learning is widely used in areas like finance, healthcare, and retail, where structured data and interpretability are important. Deep learning shines in applications that require processing large volumes of unstructured data, such as image and speech recognition, autonomous vehicles, and natural language processing. The choice between the two depends on the problem, data availability, and resource constraints. Now, let's summarize the differences in complexity. Machine learning models are generally simpler, easier to interpret, and require less data and computational power. Deep learning models are more complex, need large datasets, and demand significant hardware resources. However, this complexity enables deep learning to solve problems that are beyond the reach of traditional machine learning. Understanding these trade-offs is crucial for making informed decisions. Let's look at a side-by-side comparison. Let's compare machine learning and deep learning across key dimensions. Machine learning is best for structured data, smaller datasets, and when interpretability is important. Deep learning excels with unstructured data, large datasets, and complex tasks. Machine learning models are faster to train and require less hardware, while deep learning models demand more resources but deliver higher performance on challenging problems. Each has its place in the AI landscape. Choosing between machine learning and deep learning depends on your specific needs. Consider the type and amount of data you have, the complexity of the problem, and the resources available. For straightforward tasks with limited data, machine learning is often the best choice. For complex problems with abundant data, deep learning may offer superior results. It's important to weigh the pros and cons of each approach before making a decision. In practice, many solutions combine elements of both machine learning and deep learning. For example, machine learning models might be used for initial data processing, while deep learning handles more complex tasks. Hybrid approaches can leverage the strengths of both methods, providing flexibility and improved performance. As AI continues to evolve, we can expect more integration between these techniques. Industries are rapidly adopting both machine learning and deep learning to gain a competitive edge. From personalized marketing to advanced robotics, AI is transforming the way businesses operate. The demand for skilled professionals in both fields is growing, and organizations are investing in research and development to stay ahead. Keeping up with industry trends is essential for anyone interested in AI. Learning about machine learning and deep learning has never been more accessible. Online courses, tutorials, and open-source tools make it possible for anyone to get started. Whether you're a student, professional, or hobbyist, there are resources available to help you build your skills. As the field evolves, continuous learning will be key to staying relevant and making the most of new opportunities. As machine learning and deep learning become more powerful, ethical considerations are increasingly important. Issues like bias, fairness, and transparency must be addressed to ensure that AI systems are used responsibly. Researchers and practitioners are working to develop guidelines and best practices for ethical AI. Staying informed about these issues is crucial for anyone working in the field. Artificial intelligence, powered by both machine learning and deep learning, is reshaping society. From healthcare and education to entertainment and transportation, AI is making a significant impact. Understanding the differences between machine learning and deep learning helps us appreciate the technology behind these changes and prepares us for the future. Let's wrap up with some final thoughts. Sum up: machine learning and deep learning are both essential parts of the AI landscape. Machine learning offers simplicity, interpretability, and efficiency for many tasks. Deep learning brings power and flexibility for complex, data-rich problems. The choice between them depends on your goals, data, and resources. By understanding their differences, you can make better decisions and unlock the full potential of AI. Future of AI is bright, with machine learning and deep learning driving innovation across industries. As technology advances, we can expect even more powerful tools and applications. Staying curious, learning continuously, and adapting to new developments will be essential for success in this dynamic field. Thank you for joining us on this journey through machine learning and deep learning. If you're interested in learning more, there are plenty of resources available. Online courses, books, and tutorials can help you deepen your understanding of both machine learning and deep learning. Joining communities and attending conferences is also a great way to stay updated and connect with others in the field. Keep exploring and building your knowledge. We've covered a lot of ground today, from the basics of machine learning and deep learning to their differences in techniques, applications, and complexity. Both approaches have unique strengths and are shaping the future of technology. By understanding when and how to use each, you can make informed decisions and contribute to the exciting world of AI. Thanks for watching, and stay tuned for more insights into the world of artificial intelligence.